Welcome back to IDIS 343. In parts 1 and 2, we looked into random demand. We built the news vendor model, found the critical ratio, and pushed it through discrete demand and multiple periods. Today, we actually get to the workhorse, the lot size reorder point system, the Ch4 policy. Now, this is the model inside most commercial software. We'll lay out the assumptions, build the cost function piece by piece, then work through an example. Now, you've actually seen this picture before. With known demand, EOQ with the positive lead time gives, again, that clean sawtooth. Inventory drains in a straight line. And when it hits the reorder point R, we place an order of size Q units, which land one lead time later. But notice, in that deterministic world, only Q was a real decision. R just sort of fell out of the math. You took Q, lambda, and tau, and R was more or less determined. Basically, nothing to optimize there. Well, demand uncertainty changes the game. Look at this curve. It's not a straight line anymore. It kind of wiggles down because obviously demand arrives randomly. We order when inventory touches R, and stock jumps by Q1 lead time later. Now again, Q and R are both decision variables chosen together, right? And here's why we can't just recycle the multi-period news vendor. It ignored two things, that every real system has: no setup cost for placing an order and no positive lead time. The Ch4 model brings both back in. One note though, Q here is the amount ordered, not an order up to point. The Ch4 inventory policy falls under continuous review inventory management because inventories are reviewed by computers constantly, and whenever our inventory position drops down to R, we place an order of size Q. Alright, the ground rules. First, continuous review. We know the inventory level at all times, like a barcode scanner watching every sale. Second, demand is random but stationary. We can't predict it, but its expected rate, lambda units per year, holds steady, right? Third, there's of course a fixed positive lead time tau. Fourth, the capital K dollars of setup per order, H to hold a unit a year, C per item, and P per unit of unsatisfied demand, the shortage or penalty cost. Remember, express everything in the same time units, usually years. Here we have time units for demand and demand standard deviation. Then H, inventory holding cost, and for lead time. Okay, now we build the cost function one term at a time, starting with setup. Call T, the expected cycle length, the time between successive order arrivals. We pay K, of course, once per cycle. Over a cycle, we order Q units, and on average, demand consumes Q, conservation of units, nothing fancier. That gives Q equals lambda T, in other words, T equals Q over lambda. Divide K by T, and the average setup cost per unit time is K lambda over Q. Same shape as the EOQ world. If we use some number examples, if Q is 100 and lambda demand rate is 20 per day, T is equal to 5 days. If the setup cost is $200 per order, average setup cost per unit time is 200 times 20 divided by 100, which will be $40 per day. Holding cost next. Expected inventory now swings between S and S plus Q, where S is the safety stock. Safety stock is type of inventory we keep in the system in case demand is higher than our expectations or there's delay in delivery time. For example, we may have demand of 20 units per day. In 5 days, we expect to sell 100 units. Because demand is random and fluctuates, it is possible that we sell more than 100 units in 5 days. So safety stock covers for us. Similarly, let's say our supplier usually delivers in 5 days, but what happens if it delivers in 6 or more days after we place the order? So safety stock is additional inventory we keep for such situations. Formally, S is the expected on-hand inventory just before an order arrives, R minus lambda tau. Think about it, you reorder at R, and over the lead time you expect, after all, to sell lambda tau units. Whatever's left is basically your cushion. Average the sawtooth. Expected inventory is S plus Q over 2, R minus lambda tau plus Q over 2, multiply by H, And you see that's the holding cost per unit time. Strictly speaking, that's an approximation, but when shortages are rare, it's plenty accurate. Okay, what about the proportional order cost, the C per item? Over the long haul, units in equal units out, and on average we replenish at the demand rate. The expected proportional cost per unit time is just lambda C. And look at that term, frankly, no Q, no R anywhere in it. It's a constant, and constants, of course, don't move the optimum. We can drop it entirely. One caveat though, C again sneaks back in through the side door because holding cost is usually H equals I times C. Now the painful one, the penalty cost. The only window where we're exposed to shortages is, of course, the lead time between placing and receiving an order. If demand over the lead time, call it D, exceeds R, well, we come up short. The expected shortages in one cycle, N of R, the expected value of max of D minus R and 0, as an integral that's x minus R times f of x dx from R to infinity. Alright, divide by the cycle length, and shortages per unit time are basically lambda n of R over Q. Price each one at P, and the average penalty cost is P lambda n of R over Q. Put it together and we get G of Q and R. H times the quantity R minus lambda tau plus Q over 2 plus K lambda over Q plus P lambda n of R over Q, holding, setup, penalty, and in that order. Minimizing gives, two linked equations. Equation 1, Q equals the square root of 2 lambda times K plus Pn of R all over H. Equation 2, 1 minus f of R equals QH over P lambda. Q depends on R and R depends on Q. We kind of bounce back and forth until the numbers settle. And for normal demand, there's thankfully a shortcut for N of R, sigma times L of Z, the standardized loss function, R equal to sigma Z plus mu. Alright, time for an example. Harvey's specialty shop sells international gourmet foods. One item is a popular English mustard. It costs him $10 a jar. With a 6-month lead time, he uses 20% annual interest for holding costs. If a customer asks for the mustard when he's out, he figures the loss of goodwill at $25 a jar, and bookkeeping per order runs about $50. Over a 6-month lead time, he sells 100 jars on average, standard deviation 25, and will naturally treat demand as normal. The question, is simple. How should Harvey control the replenishment? Alright, first, units, remember everything again on the same annual clock. 100 jars per 6 months means lambda equals 200 per year. H is 0.2 times 10, $2 per jar per year. K is 50, P is 25. For the first pass, we ignore N of R, and the EOQ is the square root of 2 times 50 times 200 over 2. Exactly 100 jars, our Q0. Plug into equation 2. Let's see. 1 minus F of R0 equals 100 times 2 over 25 times 200, which is 0.04. F of R0 is 0.96. The normal table gives Z as 1.75, and R0 is 25 times 1.75 plus 100, 144. From the loss table, L of Z is 0.0162, and N of R is 25 times that, at about 0.405. Okay, round 2. Q1 is the square root of 2 times 200 times 50 plus 25 times 0.405, all over 2, about 110. Not within a unit of 100, no stopping yet, of course. Equation 2 with Q1 gives 1 minus F of R1 equal to 0.044. Z drops slightly to 1.70 and R1 becomes 143. The loss table now gives L of Z as 0.0183. N of R is 0.4575. Q2 comes out to 111 within 1 unit of 110. Converge to R2 stays at 143. The optimal policy, when inventory hits 143 jars, Harvey orders 111 more. A quick word on the tables because, well, exams happen. Table A1 gives the area under the standard normal curve between 0 and Z. The shaded slice in the picture. For f of r equal to 0.96, you hunt the body of the table for, an area of 0.46, and the closest z is 1.75. That's the lookup we just did. And its partner, the standardized loss function table. For each z, it lists L of z, basically the expected shortage in standard deviation units. At z equal to 1.75, you read 0.0162. At 1.70, 0.0183. Those are the values we pulled for Harvey. Notice the table, of course, also covers negatives. That's for, the negative safety stock cases. We'll meet later. For the example we solved earlier, in step 1, z value was 1.75. So loss value corresponding to this z value can be read by finding 1.7 on the z in the rows and then 0.5 in the column. As you will see, it is 0.0162. Similarly, loss value for 1.0 is 0.0183. Do not hesitate to review your stats course notes to remember these. Last piece, what does this policy actually cost Harvey? Safety stock is R minus lambda tau, 143 minus 200 times 0.5, 43 jars of cushion. Annual holding cost, $2 times 43 plus 111 over 2, about $197. Setup 50 times 200 over 111, $90 and change. Penalty, 25 times 200 times 0.4575 over 111, about $20.60. Well, call it $308 a year, all in. And the cycle time T is again Q over lambda, 111 over 200, about 6.7 months between orders. Next time, we ask what happens when nobody can tell you and we swap the penalty cost for service levels. Thanks, and gig 'em.